joining us from Houston, Texas. He is representing the Johnson Space Center Amateur Radio Club. I participated in a meeting with them and invited him to join us today.
Oh, welcome.
Oh,
Thanks for
wonderful.
joining.
Welcome.
How y'all doing? Thank you.
Does he want to send in any dues money?
I don't think so.
Oh,
We'll take anybody.
you know, I'm the treasurer, so I have to ask those questions.
And by the way, Phil, if at the end of the meeting you have a chance to hang in behind, I have a technical question.
Certainly.
Thank you.
All right. Well, thanks for the reminder to start the recording. So we got it going this time. So can you see my slides here?
Yes.
All right. Cool. All right. Well, thanks everyone for joining. We've got a interesting presentation with a guest speaker going to join us tonight, Dr. Jeff Love from the USGS. First, we should do like our regular roundtable stuff and get started. Phil, do you want to do the regular membership update and treasury update if you have one?
Absolutely. I have, of course, both. Our treasury is currently sitting at $8,891.85, of which 3441.62 is in our repeater fund. And I can bring up the membership list if you would like to see that.
Sure. Yeah.
Let me see if I can get down here and share the screen. There's a share the screen. Nonetheless, we have 122 of 145 members paid, so we're in pretty good shape.
All right. And Carol, you had an update on the website for us?
Certainly, I'm going to share the screen here too. This is Carol, KP4MD, and webmaster. Let me go ahead and bring it up. Okay, here's a report for the month of April for our website, which is n6na.org. I just remind everyone that n6na.org is our website, and it has all the information about the club. And it's updated pretty regularly. As far as the activity for the past month of April, we had an increase in total page views from 2,047 in March up to 2,640 in April, and we suspect this probably has to do with people being in lockdown, spending more time on the web and more time using media. The peak views was actually on Wednesday, April 8th, which was the day that we posted the last general meeting to the web. So people are apparently visiting there to take a look at our meeting. The most active web pages with a home page with 838 page views. The magnetic loop page was 292. The 10-meter page was 191. The virtual meeting page was 132. Although we only had way fewer participants last time and a lot more this time. A repeater page, an about us page, and a 10-meter net page also. As far as how people were getting to our webpage, 42.7% were finding us through Google searches, and 35.4% were going directly to our URL, which is n6na.org. And we have visitors from all over the world. Most of them, of course, come from California. There was 1,847, 43 from Washington State, 41 from New York State, 36 from Texas, 29 Virginia, Arizona had 27, and the rest from many other countries throughout Europe, South America, Africa, and Asia, and Australia. So we're very well visited. Just to remind everyone that our net schedule and all of our net information is posted on our net page. And I do want to give a welcome to a couple of new net control operators. Sean, KM6NFO, and also Jojo, KN6 Hotel Tango Delta, I believe. And they're going to be joining us on the net control roster. Just also remind everyone that our swap page has items for sale and items for want. And this is a benefit that all of our club members can participate in. And a reminder, if you need anything to be posted on the web or you have any feedback for our web, please send us an email at contact@n6na.org.
Yeah.
Were there any questions?
Is
I
it
have a
too loud
question.
for folks out there?
Not for me.
Okay.
Okay, so I'm going to stop sharing and thank you very much.
I have a question, Carl.
Yes.
This is N6KN. Have you ever considered monetizing the pages for another way of revenue support for the club?
Monetizing, well, I know you could do that on YouTube, but you mean, me putting advertisements on the pages?
Right.
I don't know if we really wanted to do that. It's something that the board of directors would have to decide. I personally don't like pages that are cluttered with ads.
I just
I'm
thought
with
since
you.
there's quite a bit of traffic there, especially on the loop one, maybe put some type of ham radio related ad and get some type of revenue that way.
Oh, that's an option. Let's go ahead and we'll discuss that in the board of directors. And thank you.
Or maybe look for a ham radio sponsor, like a vendor or something.
Okay, that's the end of my report. Thank you.
Okay, thanks, Carol. And yeah, we'll discuss that when we next have a board meeting. That's a good idea. We can talk about that. All right. Do we have any other items of interest or any other news items before we get started with our main presentation?
None for me.
All right, sounds good. Okay, so I'm gonna try and mute everybody before we hand it over to Jeff, and then make sure, I think Jeff, you can unmute yourself when you start talking. Let me just press the mute everyone button, and then we'll hand it over to our guest speaker tonight, Dr. Jeff Love. So hand it over to you.
So let's see, so I maybe press share screen and press on my presentation. Okay, can everybody see that all right?
Yes.
Yes. Good.
Hey, thank you. Hey, I want to thank Sylvia Stork for inviting me. Sorry, I don't know what her handle abbreviation is. But you know, really, this is an honor. I'm happy to present to such an interesting audience. I can already tell there's, you know, a level of technicality, but probably just general interest in, you know, technical issues. So happy to be here. Anyway, my name's Jeffrey Love, and I work for the U.S. Geological Survey, the geomagnetism program. And I'd like to talk to you today about some recent work that we are pursuing. And the title of my talk is Down to Earth with an Electric Hazard from Space. This is work that I need to emphasize involves a number of people in my program, Anna Kelbert, Josh Rigler, Ben Murphy, somebody who used to be in my program, Greg Lucas, and Paul Bedrosian, who's in another part of the USGS. This subject brings together science that's related to the space environment that surrounds the Earth. It's related to the solid Earth beneath our feet. So the USGS has a relevance in this area. And it also is related to a technology that's important for modern society, that is electricity. And we're interested in this case in how it is that space weather can interact with the Earth and cause a hazard for the electric power grid system. This work is motivated by a very nice program within the US government. It's a program that's organized out of the White House. It's been that way since the Obama administration, and it continues through with the Trump administration. It's a program known as the Space Weather Operations Research and Mitigation Working Group, which is part of the National Science and Technology Council. I participate in these meetings. I don't have a leadership role. That's kind of above my pay grade, but it's very interesting. And it's a very nice example of how when the administration wants to, they can motivate interesting projects which transcend different departments and different institutes within the government and cause them to motivate them to work together for the betterment of society. So I think that's a good thing. And I have this very pretty picture here in the background that shows the Northeast United States from space at nighttime. It's a very beautiful demonstration of the importance of electricity to modern society. And there's a little hint of space weather there. Off on the horizon, you can see the aurora borealis. So that is a product of the dynamic interaction of the sun with the earth. So we'll get to that. All right, in fact, we'll get to it with this slide here. So this is a cartoon demonstration of a dynamic instance in space weather. Basically, we have the sun, which is an electrically conducting, self-sustaining dynamo that have magnetic fields. Those magnetic fields are concentrated oftentimes into spots, sunspots. We can see them through telescopes and sometimes with our naked eye. Those regions amount to concentrations of magnetic energy, which are occasionally abruptly released, and that causes an emission, injection of plasma that is electrically conducting material from the sun, which travels outwards, and occasionally it arrives at the Earth and can interact with the Earth's magnetic field. This coronal mass ejection, as it's called, compresses the magnetic field on the day side and extends it on the night side. And then occasionally within the magnetic field of the Earth that surrounds the Earth, there are abrupt rearrangements of those field lines, and that can cause, as right here, the projection of electrically charged particles into the Earth's atmosphere, causing aurora borealis. This whole period of disturbance for the Earth's magnetic field is what we call a magnetic storm, and it can last for a day or two. They don't occur all the time. Sometimes they're small, sometimes they're big, and when they're big, they can be a problem for technological systems. So there it is. That's the kind of cartoon depiction of the space environment, which is of relevance to this subject. And in this diagram, I schematically show you an issue that's important for the issue that we're addressing here. That is how it is that the Earth's magnetic field, disturbed during a magnetic storm, like in that previous movie, generates electric currents. So time-dependent magnetic fields by Faraday's law can induce electric fields, and they can induce electric fields in the electrically conducting medium of the Earth beneath our feet, which is what's depicted here. So let's see, I guess I can point to things with my cursor. These gray lines are demonstrating the magnetic field that's generated by a current, which is this red vector here, in the space environment surrounding the Earth. So if this current is time dependent, then the magnetic field is time dependent, and that time dependent magnetic field can in turn induce electric fields in the electrically conducting Earth. Now, it turns out that the Earth is not homogeneous. It's very complicated. Every geologist knows this. Some places are essentially very good conductors, and other parts of the Earth are poor conductors. They're resistive. So this electric field that's generated in the Earth by the dynamic magnetic storm is sometimes dissipated in parts of the Earth that have high conductivity. So the electric charges can flow very easily in a good conducting portion of rock, and that has the effect of essentially dissipating the electric field that's being generated by this magnetic field. So the electric field that's generated by the magnetic field, a little bit ironically, but it makes sense, is actually stronger in parts of the Earth which have low conductivity. All right. Now, if you imagine you have a power grid, like is demonstrated here, that is deployed across a region of the Earth of low conductivity, the electric field is strong there. The charges are not flowing very easily, however, and so electric charges not responding very well in this low conducting region, find an easy path for transmission, and that is through the ground connections of the power grid. So this is how it is that a magnetic storm, essentially talking to the Earth, generating electric fields and driving currents, can drive an electric current in a grounded power grid system. That's a problem for the electric power grid because, as you know, electric power transmission is all about controlling currents. And this is an uncontrolled current in a system which is designed for controlling currents. And furthermore, it's a quasi-DC electric field, quasi-DC electric current that's being driven in a system which is designed for alternating current. So that presents a number of problems for the operation of an electric power grid. And just to kind of visually demonstrate that this really is a problem, this is a high voltage transformer depicted there on the left. Transformer experienced problems during a big storm in 1989, and it actually ended up having, as shown here, overheating of the power of the transformer, and that had the effect of burning off the insulation and frying the windings in the transformer. Basically, the transformer was taken a few storms of prominence. Some of you may have heard of some of these. The March 1989 storm was a storm for Canada. It didn't cause widespread blackouts, but caused the operators some headaches during this storm. If you go back in time, there is a very famous magnetic storm that some of you might have heard of, the September 1859 Carrington event. It's in some ways the strongest magnetic storm ever recorded. A long time ago, we had magnetometers in those days, very simple analog systems, but very capable of measuring magnetic field variations. This storm, turns out, was so large that magnetometer systems in operation at stations around the world then couldn't record its full extent. The storm was strong enough to take the light trace that was used in the recording of the storm, took it off the edges of the photographic paper that was recording the actual variation in the field itself. So we don't really know how strong the storm was at most stations, with the exception of one station in India, where they were actually still making measurements by eye. So in those days in India, they actually employed somebody to make measurements every 15 minutes of the Earth's magnetic field visually. And that turns out is the one record we have of a complete record we have of this particular storm. That record, though, is very useful, indicates that the magnetic field was very active, and that was demonstrated by the fact that aurora borealis were visible across a wide range of latitudes, down to much lower latitudes than one normally sees aurora. So you could, for example, see aurora in Hawaii, in Italy, and Cuba. So that's another indication of the intensity of this storm. And the effect that it had on technological systems of relevance then were for the telegraph systems that were in operation, and it caused widespread disturbance to these systems. Telegraph wires are also grounded and picked up the stray currents, just like can happen in modern power grid systems, like I was discussing in a couple of slides ago. So in the context of this, then, there have been some analyses, let's see, of what could be the effect on modern society if we were today to have a revisiting of a magnetic storm like the Carrington event of 1859. And it's understood that a storm of that intensity would cause widespread interference, not only to the radio signals that you folks are interested in receiving and transmitting, but it would wreak havoc with military and civilian satellites, cause widespread disruption of GPS and interference to geophysical surveys, and could possibly cause widespread loss of electricity, possibly for months, even on a continental scale. So this would be a rare but significant event, all right? And even though it's rare, the widespread significance of such an event means that the risk is actually rather high because the cost would be quite high for society. It's estimated that if we had a revisiting of the Carrington event, the economic impact for the United States could be $1 to $2 trillion and $2 to $3 trillion globally. You know, I was putting the slides together, and given everything that's gone on with the COVID virus, you know, a couple of months ago, I would have thought $1 to $2 trillion was a lot of money. Trying to rescue us from the COVID virus, $1 to $2 trillion. Well, it's not as much as it used to be, it seems, but still a significant impact and worthy of investigation. All right, so I want to briefly explain the science that we're doing, and I'll explain it with this kind of schematic diagram here. Some of this is familiar to you folks. On the top, I'm showing just as a simple set of concepts. You have an input signal right here, and that is passed through a filter, and you have an output signal. And that filtering process is a process, time series operation that we apply to the input signal called convolution. So there's a filter that is convolved with that time series, and that gives us the output. That's the abstract concept that we're working with here. So in our case, the issue that's of relevance here is right here. We have geomagnetic field variation driven by the sun. That geomagnetic field variation interacts with the electrically conducting solid earth to give us an electric field, and that's that electric field that's of interest to the power grid industry. So in effect, the solid earth is the part of this that is acting like the filter. It's that electrical conductivity structure, which gives it a filter process. We refer to the surface impedance of the earth, and we convolve that impedance with the magnetic field variation to get a geoelectric field variation. So that's what can happen physically. Now, if we were to deploy magnetometers, as we have across the surface of the earth, we can measure the Earth's magnetic field variation. And if we insert voltmeters into the solid earth, we can measure voltages and electric fields that are induced in the earth. So in effect, measuring the input and the output of this process, and with the input and output, you can make inferences as to the, you can derive the impedance of the earth, and from that surface impedance, you can infer the electrical conductivity structure of the earth. That's an inverse problem. That's not what we're talking about today, but that's what some geophysicists are interested in, and I'll discuss that right down here. So we have geomagnetic field variation recorded at stations, and this is a picture, whoops, of one of our USGS stations in Fredericksburg, Virginia. It's an old observatory where we have buildings much bigger than we need for modern magnetometer systems today. But that's one of our stations. We're measuring the magnetic field. And down here, these fellows are deploying magnetotelluric sensor systems. They are measuring the electric field and the magnetic field to make inferences of the impedance. The first interest for that is to understand earth conductivity structure, but if we have the impedance, we can take the magnetic field, convolve it with the impedance, and make estimates of the geoelectric field. So we have long records of geomagnetic field variations. We have those from long periods of making, essentially monitoring the magnetic field over decades of time, take those long time series, convolve with the surface impedance, and we can reconstruct a history of geoelectric field variation at all of these impedance, at all these sites where impedance was effectively measured. So it's this combination of magnetic field monitoring, magnetotelluric surveying that allows us to reconstruct a history of geoelectric field variation across the United States. So that's what we do. We take those data and we analyze them, and just to briefly discuss here, these are time series. And in this case, on the top here, I'm showing magnetic field variation recording a magnetic storm, one that occurred in 2003. And you can, some analyses are interested in first differences, essentially the time derivative of these time series. And it's these magnetic field time series convolved with the Earth, which give us the electric field, which is displayed right here at the bottom. In this case, these are direct measurements of the electric field. And like I say, the combination of the electric field and the magnetic field could be used to infer the impedance. And once we have the impedance, take the magnetic field, convolve it with the impedance to get the electric field. So it's this kind of time series which we analyze. In this case, it's only 3 days worth of time, but we have really long time series of magnetic field variation. We can, decades long, we can reconstruct really long geoelectric time series, and we can analyze essentially the history of geoelectric field variation across the United States in this way. We then analyze the statistics of this geoelectric field variation and do some extrapolations in order to understand what it would be like if we had a once in 100-year magnetic storm, and then we can make a map of it. So that's what I'm showing here. Now, I don't know, see, can I move this around? Yeah. Okay, so I'm just moving this little box with all the people's faces in it off to the left. This is a hazard map, and this is one of the last slides I have in my presentation. This shows where across the continental United States, this geoelectric hazard is really bad and where it's not so bad. And in this case, we're making this map and estimating the electric field across CONUS, across the contiguous United States, and then projecting it on to the power grid itself. So these little lines represent power grid lines, and if they are bright yellow, that means that once per 100 years, a magnetic storm is inducing a powerful voltage on those particular lines. And if they're dark, they're inducing a less powerful voltage. So I just want to emphasize that some places have essentially a high hazard, like up here in the northern Midwest of the United States, and also along the eastern seaboard of the United States. This is related to 3 different factors: the level of geomagnetic activity, so a magnetic storm, and the local surface impedance, which is in turn related to the electrical conductivity of the rocks beneath the surface of the Earth. And then finally, the other factor is the topology or the geometry of the power grid lines themselves. All of these factors have been put together to allow us to reconstruct this hazard map. So what this map shows us is that, again, hazards are high in some places and low in other places, and it quantifies that hazard. It is a useful product for the power grid industry as they evaluate their systems and try to understand where they need to make their power grid systems more resilient and where they don't have to worry about the hazard as much in other places. This is a result of several years worth of work. It has important implications for national security, and I'm happy to say that we've received a certain amount of popular press, and I'll just list them here at the bottom, and there we are. So, let's see, I just want to say one more thing. This voltage ranges from about 1,000 volts to something far less than 10 volts. 1,000 volts on quasi-DC on the power grid system is far more than enough to actually damage the transformers designed for alternating currents. And for some reason, I'm not being able to, okay, I can change my slide there. There we go. All right, so just move on to my conclusions. From this analysis, we understand that the North American Electric Reliability Corporation, which is a consortium of power grid companies, they've been doing their own evaluations of what it would be like if we had a 100-year storm. They have a standard that they've been using of 8 volts per kilometer. And we now know from these maps that 8 volts per kilometer is too high in some places. The standard is too high, and in other places it's too low. In other words, if the power grid companies are using 8 volts per kilometer as their standard. They're spending too much money to make the systems resilient in some places and not enough money to make those systems resilient in other places. So the fact that we now have a map showing the geography of this hazard allows them to now focus their resources to in an appropriate way. Here, let me back up here. One thing that you might notice here is that there's this region in the southwestern United States, which is incomplete. And it's incomplete because we haven't finished all of the surveying that needs to be accomplished in order to estimate the impedance of the Earth. So it's for this part of the United States, which is still a work in progress. The work that we've done so far demonstrates the importance of that work. So this work will continue. In fact, this year, the USGS received some money in order to continue this surveying. So I just want to say that that magnetotelluric survey needs to be completed. And the nation, in my opinion, needs to improve its geomagnetic monitoring. We have 6 stations in the contiguous United States, and really that's the sparsity of those stations, which is the main limitation on the accuracy of the maps that we make. And then finally, if all of these products are put together, it is conceivable that we could not just do essentially a statistical map of geoelectric hazards, but we could also make real-time maps of geoelectric hazards, which could be produced in real time to show how magnetic storms are affecting the power grid systems. And that would allow power grid companies to use those maps. They could use those maps to make operational adjustments to ensure the reliability of their operations. So with that, I'm happy to take questions and offer up some answers. Thank you.
Great, thanks, Jeff. So if anyone has any questions for Jeff, you can unmute yourself to ask a question.
I have one.
And unmute.
Are you ready for a question, Jeff?
He's muted. Unmute, Jeff.
Okay, there I am. I think I'm unmuted.
Yep, there you go.
Okay. Yes, somebody has a question, sorry.
I have actually 2 questions.
Okay.
I think the first one you've already answered. I was judging from your map. I thought we all should move to Texas. So the question, well, we really don't know then. I was going to ask if Texas would be considered a high or a low impedance zone.
Yeah, we don't know that yet. You know, I think it's going to be complicated, frankly.
Sure.
There's a lot of sediment there.
Well, not only that, you know, Texas has a huge wind farm system.
Mm-hmm.
It's remarkable how big that thing is. Deb and I drove through that area a couple of years ago, and that wind farm must be, you know, 4 or 5 miles by 4 or 5 miles. It's massive.
Oh, I bet, at least.
But the other question I had, this DC energy, I'm sure it's in the form of a pulse since it revolves around sunspot activity. Do you have a rough idea what the duration of one of those pulses typically is?
Yeah, so this map that we're showing is showing 1 minute duration voltages.
1 minute.
That's right.
So those pulses are in that order of a minute?
Well, the magnetic activity, let's just back up here. This is a depiction of a magnetic storm over 3 days worth of time. This instant right here, this abrupt change is the start of the storm, but you see that the storm evolves and has different levels of activity at some times and more quiescent at others. The storm is not really just an impulse. It is activity across a wash of frequencies, and all of those frequencies are, when you add them all together, you get the time series. And when you convolve them with the impedance, you get the geoelectric time series.
Yeah, but isn't it true that
it's sometimes impulsive? But you know,
isn't it true though that when you're trying to induce a voltage due to a field, it needs to be a changing field to induce that voltage?
It is, and this is a time-dependent magnetic field, and that's the reason it's doing the induction. That's right.
Okay. Those are my questions. Thank you.
Yeah, very good. God, it's jog my memory here. We don't know what the surface impedance of Texas is really until we measure it. It's true that there's a lot of sediments there, so those tend to be low impedance, high conductivity rocks, which tend to be low hazard. But there depends on the thickness of the hazard or thickness of the sediments and the underlying geology as well. One point that, and I thank you for that question. One point that I forgot to emphasize, I want to emphasize it. Why is the high hazard here high in the eastern United States? Why is it high in the northern Midwest? And it's because there's electrically insulating rocks in those regions. Sure enough, there's a thin layer of sediment overlying much of that insulating rock, but it's just so thin that the magnetic field variation just diffuses right through it and doesn't see it. There are also very long lines in the northern Midwest United States, and so when you take this kind of weak electric field and integrate it along the 100, maybe even several 100-kilometer long line, you end up with a lot of voltage on that line. Over here in the eastern United States, the lines are rather short, but the rock underneath is actually quite insulating. In fact, this high hazard region corresponds to a geologic structure known as the Piedmont. It's very old, metamorphic and insulating, very dry rock, so it's very poor conductor. And it's worth recognizing that that's where an awful lot of the population of the United States resides. And so it is interesting that there is a high hazard where we have a very high concentration of population. So
does that account for all of the lightning activity that seems to occur in that part of the world?
No, this is not related to lightning. Lightning can affect power grid systems. They've done a pretty good job of making them relatively resilient to lightning. Lightning, of course, has a very high frequency content, much higher frequency than 1 minute that we're talking about here. But yeah, lightning can induce very localized, very high frequency variations in the electromagnetic field and can affect technological systems kind of on a localized scale.
Well, the reason I asked the question,
mm-hmm.
the reason I asked the question is in the West, we rarely have concerns about lightning.
Yeah, well, I can tell you, living
but in the
Colorado,
East, it's a very common situation.
That's right.
So I
and
just thought there might be a correlation here.
No, there isn't. But I can tell you, I live in Colorado, and we actually have a fair amount of lightning, probably related to the Rocky Mountains. But that's a different hazard, and it really physically is just not related to what we're talking about here.
I think, Mr. Love,
yes?
I think what we're saying is that we know that the electrical grid's pretty well protected from lightning.
Yep.
But as ham radio operators, throwing an antenna up in the air, we're not. And what we're saying is, like, I grew up back east, and let me tell you, some of those lightning storms are apocalyptic, and they last for hours. They do a heck of a lot of damage to trees, not so much the electrical grid. And so what we were saying is, does the conductivity of those rocks have something to do with the horrible lightning strikes we get versus the almost none that we get in Sacramento?
Yeah, I'm going to have to say I don't know the answer to that question. I don't know very much about lightning, and I don't know what the measures are that power grid companies take to make their systems relatively resilient. One thing that's just kind of qualitatively different between lightning storms and what we're talking about here, lightning storms, of course, occur fairly often. What we're talking about here is a really low frequency event, once in 100 years. And the phenomena of how the magnetic field induces electric fields, in this case, on continental scales or kind of regional scales, the size of an entire state, is very different dynamically for a power grid system than for a lightning strike, which would be a very localized effect. That's all I can say, but I don't really know the ins and outs of how power grid systems handle lightning.
Yes, I have a question. My name is Carol Malazzo, Dr. Love. I don't know if you know Dr. Tamitha Scove. She's a PhD in geophysics and planetary physics, who's beloved by the amateur radio community because she shares all kinds of information about geomagnetic storms and the ionospheric propagation, which is very relevant to our operation.
Yes, the space weather woman.
Yes, very much.
I know her.
Well, I really appreciate everything you shared here. Many of us have observed, for example, we have a group of our club members that gets on a frequency of 28 megahertz, it's 10-meter band on Wednesday nights for net. And we notice that when the K index and the A index are high, we have geomagnetic storms. And there is a general increase in the background level of radio noise. And I expect that that has something to do with random conduction going up there in the plasma there of the ionosphere as a result of these geomagnetic storms. You think so?
Yes, that's a great way of describing it. So just, let me explain it in my terms. Basically, when you have a magnetic storm, when the magnetic field is disturbed, there are times when the electric charges in the space that surrounds the Earth are basically redirected to flow along those field lines. They flow into the Earth's atmosphere and out along another field line. And so that current has to make its flow closed, and it makes that closure through the ionosphere, the electrically conducting part of the Earth's atmosphere. Well, when you have a current that's flowing through the ionosphere, as you know, it has ohmic heating. And it heats up the ionosphere in different ways in different places and by different amounts in different places. So you get differential heating of the ionosphere, and you get differential ionization of the ionosphere. So in contrast to the state of the ionosphere during quiet times, when it's essentially kind of like a electrically conducting mirror that reflects radio waves, during a magnetic storm, the ionosphere becomes very heterogeneous, becomes very electrically conducting in some places, heated up and moving in other places, and it's not a very good mirror for your radio waves. And that's essentially what's going on. So when you have high K index, you have magnetic activity, and you're likely to have disturbance of the ionosphere.
Yes, I have one more question. It has to do with the things like the Carrington event and those kinds of pulses that you have. One thing that we're very much aware of is the concept of the electromagnetic pulse being something that can destroy a lot of equipment that's connected to antennas. And
yes,
what we're talking about here, could that also induce that kind of a current in an antenna that we?
Yeah, that's a great question.
Yes.
It turns out I'm working on electromagnetic pulse. So I've been so far spending most of my career looking at magnetic storms and the effects they can have. But if you go up to higher frequencies, and the issue that's important for the nation is the effects of electromagnetic pulse. So just to back up, if we're talking about a man-made phenomenon now, whereas magnetic storms are natural, most of the time when people refer to EMP, not always, but most of the time, they're talking about electromagnetic pulses generated by nuclear explosions. And so if you have a nuclear bomb and you blow it up in space above the Earth's surface, maybe at an altitude of several hundred kilometers, that nuclear explosion will generate an electromagnetic pulse that is, in an abstract sense, a little bit like some of the impulsive phases that you see in a magnetic storm. They are higher frequency though. Electromagnetic pulse, the discussions are usually revolving around a really early phase where you have, and by the way, when people discuss electromagnetic pulse, it's the first time I've ever seen time displayed on a logarithmic axis, because there's just so much variation across so many different time scales. E1, the early phase of an electromagnetic pulse, is really a bright, high frequency, short duration part of the explosion, as you might imagine. A lot of that, not all of it, but a lot of it gets filtered out by the ionosphere. And it's very high frequency too, and the power grid industry is uncertain, but they feel that their systems are generally resilient to the early phase of an electromagnetic pulse. It doesn't mean that there wouldn't be some effects, but large scale is maybe not concerned with that high frequency. Interestingly, they're more concerned with the low frequency part of EMP, which is a variation in the Earth's electromagnetic field that encompasses periods from about 1/10 of a second out to about 1,000 seconds. So this is a long period variation caused by the nuclear explosion. And what's happening is that the nuclear explosion is changing the conductivity of the ionosphere. It's inducing currents in the ionosphere, and those electric currents in turn generate magnetic activity that then induces voltages in the power grid system on the surface of the Earth. That last phase is sometimes called E3, and that's really the frequency range that the power grid industry is most concerned with. That is a frequency range that I'm analyzing too, in order to try to analyze and produce a map even, showing where the power grid industry might have some issues of concern. Again, the issues would be related to the frequency of magnetic field variation, the surface impedance, which is related to the conductivity of the rock, and the topology of the power grid. So it's an analogy very similar to the analysis we've already conducted for magnetic storms, just kind of shifted to slightly higher frequencies. Okay, that's kind of a long roundabout answer. We could probably talk about EMP all day, but I just wanted to give you that kind of heads up. We are working on it, and it is also a project organized by the White House among different departments of the US government.
Okay, can I just clarify the question a little bit better?
Okay,
It
sorry.
says, can a geomagnetic event be of such magnitude that it could damage the delicate solid state equipment we have in our radios connected to antennas?
Yeah, I don't think so. I don't think a magnetic storm is going to damage the solid state systems you have in your systems like an EMP might. And the reason is because your systems have such a short spatial scale. For what we're talking about here with these maps, we're talking about power grid lines that have length scales of couple hundred kilometers. Those are really long lines compared to your radio transmission lines. And so they are picking up, they're not directly picking up the electromagnetic variation. They're picking up signals induced in the solid Earth. And these are very small, feeble voltages. But when you integrate them across, or very feeble electric fields, when you integrate them across the long length scale of the power grid line, you end up with a lot of voltage. But for your lines, you have rather short lines in comparison. Not,
it's really an aperture.
All the respect, of course, but they're short, right? They're not hundreds of kilometers long lines. So you're only going to get a tiny fraction of a volt in your system induced by a magnetic storm. So,
Per kilometer.
all righty.
Jeff, this is Tom Cutter. I'm an alumni of the USGS. I used to work there. I'm also the husband of Sylvia Stork.
Oh, okay. Congratulations, and thank you for joining us. And see, I'm not seeing your picture here. Maybe I'm doing something wrong.
Well, it's very likely that there are so many people that I'm not popping.
Okay.
My question was, who are the users of the data that you're collecting other than just the grid people that manage the power system?
Yeah, well, thanks for asking that question. So we monitor the Earth's magnetic field, and let me see, I think I've got a slide here. The USGS monitors the Earth's magnetic field at several stations across CONUS, and the stations we have online right now are all these blue dots in this map right here. And those data are used by the power grid industry but they're also used for making maps of the Earth's main magnetic field. So making maps of the magnetic field is important for navigation. There's still applications which essentially use compass-based navigation. It's electronic compasses, but they use the magnetic field for orientation. For example, there's an application of using magnetic data for directional drilling for oil and gas. These days when you drill for oil and gas, you drill down and then out horizontally. And in order to orient your drill bits, you oftentimes have a little magnetometer that follows the drill bit. That magnetometer is acting like a compass, and it's measuring the direction of the drill bit relative to the Earth's magnetic field. But the Earth's magnetic field is time dependent, so you have to also monitor the Earth's magnetic field at the surface in order to work out the absolute orientation of the drill bit. So that's an application. So his main field modeling is directional drilling for oil and gas, and there's also aeromagnetic surveys that are performed for mineral exploration. Same kind of thing happens there. You want to make a map of, in this case, a map of the magnetization of the crust of the Earth, and that's different in different places. This is a permanent magnetization now. And so you fly an airplane over the geography of the crust, and as the airplane flies over, it measures variations in the magnetization of the crust. Problem is, the magnetic field's time dependent, and if you just use the data as they are, you would be mapping time-dependent magnetic field variation into the geography of the anomalies that you're measuring with your survey. So you have to subtract that time dependence, and you use a ground-based station to do that. So those are just some of the applications that the magnetic field is, monitoring the magnetic field is useful for. But thank you for that question.
Well, I had a follow-up question related to that. The USGS measures lots of data. They do a lot of Earth-based measurements. And I have read stories that people have observed magnetic field changes as a result of earthquakes. And so I was wondering if you could cross the data that is collected by the USGS for earthquakes and see that you are also seeing that in magnetic field changes,
right? So,
conductivity changes.
Another great question. So what you're talking about is what we call a coseismic signal. That is a perturbation to the magnetic field caused by an earthquake. This is a little bit different than a precursor signal, which is what some people try to find. They try to find magnetic field variations that might tell you that an earthquake is going to happen. That hasn't worked so far. But coseismic or post-seismic signals are definitely real. So what's happening there is that there's several effects that are going on, but as I understand it, the primary one is simply related to the fact that when you have an earthquake, you have a sizable displacement of the crust across quite a large spatial scale. So, a large earthquake can amount to a break along a fault of tens, maybe even 100 kilometers. And that is an abrupt change in the topography of the Earth's surface. That in turn induces a wave in the Earth's atmosphere, which propagates up to the Earth's ionosphere. And turns out, because of the way the Earth's atmosphere loses density as you go to higher altitude, the amplitude of that wave increases as you go to higher altitude. So you get a large amplitude wave in the Earth's ionosphere. That ionosphere is electrically conducting. It interacts with the Earth's magnetic field and in turn induces changes in the Earth's magnetic field, which can be measured at ground-based stations. So it's a little bit roundabout, but there's definitely a coseismic signal that follows an earthquake, which can be detected in magnetometers. In addition to that, sometimes if you have a magnetometer that's really close to the epicenter of an earthquake, the magnetometer itself shakes. And since it's moving now, it's moving relative to the Earth's magnetic field, and it shows up in the magnetometer as variation in the magnetic field. It's not a variation in the magnetic field, it's just a change in the orientation of the magnetometer. So sometimes indirectly, magnetometers act like seismometers. So there are examples of that in the data as well.
Thank you, Jeff. The corollary to that is people have observed earthquakes that cause radio propagation to stop at a particular interval. So there's a belief that certainly what you're describing is supports that that people have observed blackouts.
Yeah, I am unaware of that. I don't know that much about radio, and I apologize for that. It's interesting to hear about that, and maybe, I'm not telling you it's true, but maybe that's related to what I was describing. So,
all right, that's my questions. Thank you, sir.
Yeah, you're welcome.
Hey, Jeff, this is Sylvia. I have a question.
Yeah, hi, Sylvia. Thanks again for inviting me.
Thanks so much for accepting the invitation.
And I hope that you see that the USGS does a whole lot of diverse things.
Yep. So you were talking about the conductivity of the rocks.
Yes.
So are you actually, so is this a skin effect? Or are you talking about the soils or the actual rocks themselves?
Yeah.
How deep does this go?
Yep. It is a skin effect, but it's a very thick skin. So the soil is irrelevant. That's far too thin for the frequencies we're talking about. If you were talking about really high frequencies, soil would be a factor, like for E1 and EMP. But for a magnetic storm, where we're talking about frequency or periods that range from about a second out to 10,000 seconds, the skin depth, the diffusive skin depth for the Earth ranges from about 1 or 2 kilometers to maybe one or 200 kilometers. So it's across those length scales that the conductivity is of relevance. So as soon as you get down to a depth of at least 1 kilometer, and maybe even as deep as 100 kilometers, you're talking about rocks, bedrock. And so the effect that's important here is really deep earth geological structure.
Interesting.
It is.
Yeah.
So when I retire, can I come be a volunteer for you?
Yeah, we in this era of tight budgets, we're happy to talk about volunteers.
Yeah.
Any other questions? I'm also happy to take questions that are about parts of the magnetic field I didn't mention. I get all kinds of questions from the public, and I think it's great. So, no questions about migrating turtles?
Oh, that sort of thing, and the way and pigeons.
Yeah.
And all of
biomagnetism. Well,
how about UFOs?
UFOs, yeah. Well, this comes. I get these kinds of questions from my wife all the time, and she's interested in kind of mystical things, let's say. And I usually say, well, some of these things some things I'm more inclined to believe, just straight, and other things I just have to see it to believe it. And so UFOs, yeah, I have to see one to believe it, basically. Since I mentioned it, I'll talk about migrating turtles. This is not related to what I was talking about, but it's related to the Earth's magnetic field. In ways that I don't really understand, some animals can detect the Earth's magnetic field. I'm not sure how they do that. There's a number of theories, but I'm not going to talk about biomagnetism, but I will say that sea turtles apparently use the magnetic field for navigation. It's only one of several senses they have for navigating. I think their primary sense is smell, actually. They smell the ocean water in different ways, but some species of turtles migrate between South America and Africa. That's a long distance. And furthermore, it's interesting, sea turtles live a long time. Well, if you just imagine, if you are a sea turtle has been living for 50, 60 years, turns out the Earth's magnetic field changes over that time scale. And that's why magnetic charts need to be updated, and they're typically updated every 5 years. So if you're using a compass, you can expect the compass needle to change in quiet time absolute orientation by about 1/5 of a degree per year. Well, if you wait several decades, that adds up to fairly large declination. So that means that sea turtles, if they're using the magnetic field for navigation, have to learn. And they have to learn about the orientation of the magnetic field. And they probably kind of adjust their sense of orientation over the decades of time that they spend swimming between Africa and South America. So that's a little piece of trivia for you.
All right, Jeff. So I have another question for you.
Right.
So I recently, do you think this is all leading up to a flip in the polls, or?
Yeah, great question. So just a little bit advertising. If you go to my USGS homepage, where my professional page about me, there's a little article in there in Astronomy magazine that came out, I think it was last year, where I answered this question. So people write into the magazine and want to know about, is the magnetic field of the Earth going to flip soon? And this is something I used to study before I came to the USGS. So just to back up here, most of the time variation in the magnetic field we've been discussing today is something caused by the space environment surrounding the Earth. But the Earth's main part of the Earth's magnetic field is generated in the Earth's core. It's electrically conducting dynamo. It's essentially a naturally occurring electric generator. And as you might imagine, it's kind of complicated. The flow in the core is not steady. It changes over time. And as a result, the magnetic field that it generates also changes over time. Now, the dynamics of the core are affected by the Earth's rotation. It's one of the forces, not the only force, but one of the forces affecting the dynamics of the core. So that means that the magnetic field that the Earth generates is at least affected by the Earth's rotation. So there is a tendency for the Earth's dipole, the main part of the field, to be sort of aligned with the rotational axis of the Earth. Now, the Earth's core can generate a magnetic field of one polarity or of the opposite polarity just with equal ease. So there's essentially two states, the present polarity or the opposite polarity, that the Earth's dynamo is happy to generate. So add to that the fact that everything is time dependent, and essentially the polarity of the Earth kind of orbits in an abstract sense around the geographic pole, or it orbits around the south geographic pole. And so with this time dependence, occasionally the Earth's magnetic field kind of finds itself in kind of a wonky position, and it just ends up reoriented itself. So that's called a reversal of the Earth's magnetic field. They are not predictable. They happen, as far as we can tell, rather randomly. They happen relatively quickly compared to the history of the Earth. So just general numbers, a reversal happens on average about every 1,000,000 years. Sometimes it's every 100,000 years. Sometimes it's several million years. But on average, it's about 1,000,000 years. It takes about 10,000 years for a reversal to happen, okay? So that's about 1% of the time the Earth's magnetic field is in a state of reversal. So that's an important fact. Now, given that the magnetic field of the Earth is time dependent, we can't say that the Earth's magnetic field is actually going to flip over. Or sometimes it'll kind of almost flip over and go back to where it started. That's called an excursion. So we don't really have any capacity for predicting a reversal of the Earth's magnetic field. But even if we did, it would take about 10,000 years to happen. So we would have to wait around a while before we even knew whether or not our prediction of a reversal was even going to come true. So that makes it, let's just say, a challenging problem. So.
Cool. I didn't realize what the time scale was. That's really interesting.
Yeah.
Other questions? All right. Well, folks, I don't know. I don't want to keep you all. I'm happy to answer questions. I'll just say I once gave a lecture to a small college back in New York, and it was an event that the whole town came to. So I gave a lecture that lasted for about half an hour, and then was followed by an hour and a half of questions from the general public. And I'll tell you, it was a blast.
Wow.
If you want.
Thanks for spending the
But
time.
I also know that maybe
Thanks for spending the time with us tonight. This is a really interesting topic. I think we all enjoyed it.
You're welcome.
So
You're welcome.
thanks very much.
Yeah, thank you.
Thank you very much. Thanks for
Thank you,
inviting me.
Jeff.
And I'll just let you know that, this is the era of COVID virus. I've been spending my time at home, but I'm still doing work. And I'll tell you, the guys and gals in my group, hardworking people, taxpayer dollars well spent. It's a very small program in the federal government, but it's doing some work which is important for the nation. So, and it's my honor to help out.
Well, thank you.
Thanks very much.
Righty.
All right, we'll have a recording of the session tonight. We'll have it up on YouTube, so we'll send you a link when it's uploaded.
Okay, great. I appreciate that. Thank you very much.
All right, thank you.
Thank you.
Okay, I'm going to sign off and let the rest of you go make dinner or whatever you're going to do.
Okay, thank you.
Thank you.
Thank you, Doctor.
That does not work very good.
Looking good, Mark.
I'm just kind of playing with it a little bit here. I felt like sitting in a comfortable chair.
Yeah.
Are the eyes glazed over?
Yeah, no. I found it quite interesting. In fact, I was going to ask him when the poles flip. I'm guessing the poles don't really move. That the intensity of the magnetic field just drops down to zero and then gradually comes back up.
Yeah, over 10,000 years.
Yeah.
Right.
So it's like the poles.
That's gradual.
Really, because I understand the poles move a little bit too, but when they flip,
precession.
yeah, right. But when they flip polarity, I don't think that like swings down past through the equator like that. It just kind of like goes down and then comes back up is what I'm guessing. I don't know how it works.
Yeah.
Well, if I live through one of the cycles, I'll let you know.
Yeah. No, it's kind of interesting stuff.
Yeah. He's an interesting man. Very scholarly.
Got a good job. It's nice to get paid to do something you'd like to do anyway. Best kind of job.
Yeah.
Oh well. Anyway. Are we ready to call it a night?
Yeah, we can wrap up. Yeah.
Yeah, I'd like to remind everyone about the net tomorrow at 7:30 on the 2-meter repeater, the health and welfare net at 7:30 p.m. And then the weekly River City ARCS net will be at 8 o'clock. Sean, the KM6 NFO, will be our net control tomorrow. And then we will have the 10-meter net at 8:30, and that's on 28.420. Upper sideband, everyone is welcome to join us. Thank you.
Okay.
Thanks, Cal.
Neil, you had a question for me.
Yeah, we'll hang on for a minute after, but I don't want to bother everybody. Just a quick technical question for you.
All right. I do want to mention that our new member, Larry Foreman, has been doing quite a bit of work erecting antennas in very tall trees. And he's interested in putting together a little presentation for our membership about his efforts and how he went about it. I thought that might prove to be helpful to a number of the club's members.
Yeah.
That'd be good. Yeah.
Yes, indeed. And we always need presentations for sure.
And Carol, you indicated that there was a gentleman that you mentioned near the an airport that needed assistance in putting up an antenna on a tall tree, correct?
That's the same one. Yes.
Oh, it's the same one?
Larry, yeah.
Yeah. So
Phil, did you go out with your tennis ball launcher and give him a hand?
No, actually, I had him stop by and pick it up, and then I took him over to a park and taught him the usage of the tool, and he must have spent 10 days trying to get it done. He has one palm tree. It's got to be 80 plus feet tall.
Wow.
And once you launch a line over a palm, you know, the top of that palm tree is a jungle. And getting a line through the jungle posed the biggest problem. The launcher worked like a charm.
I imagine his neighbors were looking out their windows wondering what he was doing, shooting
tennis
from a
racket.
tree.
So it worked out well for him. He was pretty pleased with how all that played.
Nice.
Very good.
Like I said, you don't need a tennis ball launcher, just a tennis racket
Right.
and a strong arm.
And a McEnroe, yeah.
Yeah, you're gonna get it over one tree somewhere.
Someone's tree, maybe not your tree.
He developed quite a technique for it all, I'll tell you. Kevin, if Neil and I wish to chat, does this session stay active if you log out?
I think it closes if I close it.
Okay, I was kind of concerned with that.
Yeah.
Yeah.
I can set you up an extra one and send you the link if you want.
No, I don't.
No, it's not necessary. I never hear you, Phil. I never hear you on the 2 meters. I've been looking for you on the 2 meters.
That's because I'm lazy.
Well, join the club. I tell you what, do you have, what's the best email? Is it, do you have a good email on QRZ that we'll go that way?
I don't have it on QRZ. It's actually on the website, and I can give it to you right now. It's pretty easy. It's just my last name, plural, Sittners, Sittners.
Okay, hang on a minute. Sorry, guys. Go ahead.
Do you want to type it in the chat window?
SBCglobal.net. What's that?
You can type it in the chat window there.
Oh, yeah. Let me do that.
Yeah, press the
Appreciate it.
chat button.
Engine 10, time out 210, Delta 3 operations, Bravo 3.
Hi, this is Peter, KD6 Fuse at A Jump Rope. I just wanted to say hi to Neil and everybody. And I really enjoy, I participate in high school meetings and I love the speakers and I really enjoy what your club's doing.
Thank you. Thanks for joining. Thanks for joining us.
Hi there. Are we going to make any comments about field days tonight?
Uh-oh. Did I go away?
No, you're there.
I somehow managed to screw that up.
I think Jason was on earlier.
We still see you and hear you well.
Well, what happened to...
No, PL is fine. Double click on chat.
Well, I lost chat.
Right at the bottom of the window. Move your mouse over the bottom of the window. There's a chat.
Oh, let's try this. There we go.
There you go.
So chat, and what I want to do is, do I need to raise my hand to type my, trying to leave my email address. Lower hand.
Hey, Phil.
Yeah.
Don't worry about it right now. I am okay on QRZ, so if you just go there, we can go that route.
Okay, I don't have anything posted on QRZ.
Mine is there, so if you go there, you can see mine as easily.
All right, we can do that.
Thank you. Don't want to hold everybody here for that. And Bob,
what was our peak number, Kevin, tonight? Peak number?
35.
35. That's good.
Yeah.
That's every bit as good as any physical meeting we've had. I think that was about the max, maybe 36.
Yeah. We had a few other people join from other places as well, so that's great.
Yeah, I think that worked pretty darn well.
and Bob had a question whether we're going to talk about field day at all, if we have any information on that.
At this point, I don't know. Carol's kind of the best answer to that. Is there anything out of ARRL regarding field day?
No, it's just to be ready to adapt depending on the status of social distancing in your particular locality. So it's up in the air where we're going to be at that point.
Well, I sent a note out to Jason asking him how he's doing with it. And his response was he thinks everybody should be prepared to do field day in their own backyard. And I suspect that may well prove to be the case. We're just going to have to see how it fits together. It's getting kind of late in the day.
So if we do that, Carol, do you know, will we still use the club call sign? Have the ARL put out any guidelines about how clubs will still participate, or do we just do it individually?
The rules are you have to be, I believe, within a 1,000-foot radius to be counted as one club for purposes of scoring.
Got it.
So that wouldn't work.
Right. Okay. So it'd just be individually.
Well, 1,000-foot radius divided by 6 feet separation. We can't put a lot of people there.
All right.
I'll
send you a note, Neil, and we can.
Good enough. No hurry at all. No hurry at all. Thank you, gentlemen. Appreciate it. Was a great presentation. I really appreciate it.
Thank you.
That was a very interesting topic.
It was very good. Thanks, Sylvia, for getting him involved.
Yeah. Yeah. Hooray, Sylvia.
I wonder how many glazed eyes we had. It was pretty intense stuff.
It was. It was interesting.
Depending what minute in the presentation you're talking about.
Yeah.
Yeah, the topic for next month is solid state transformers.
That is
art is going to be
that's
giving.
art. Yeah.
Yes. Yeah. That's going to be interesting.
Yeah. It's kind of nice to get topics that are a little mentally challenging and allow us to actually learn something and not just, big deal one other style of antenna, It's nice sometimes to just actually learn something.
Yeah, it's true. Yeah.
Makes my head hurt.
Poor baby.
All right.
I always enjoy learning new things, so yeah, and I got some of it I followed, a lot of it I didn't, but now I'm gonna learn a little bit more. I like to learn about topics and then learn more, so I really appreciate this.
Yep.
All right, everybody. I'm going to press the button to wrap it up.
All right. Thanks, folks. I enjoyed it.
Guys.
Right, thanks.
Okay, 73s to all of you.
Right. Take care. Stay safe.
Good night, all.
Okay, good night.